So now we're going to look at Hess's law. Okay, now what exactly is Hess's law? To understand this, let's say let's draw an energy diagram. Okay, so here I have energy on the y-axis. Okay, and we're not drawing a full reaction profile. Okay, but let's say that over here I have some substance A. Okay, I have some substance A over here. Okay, so that's my starting point, right? And what I do is I take that substance A and I react it in some way to convert it to substance B. Okay, I react it to convert it to B. And here, of course, I'm showing an upward arrow, which means that energy was needed for the conversion from A to B. And let's say that the energy needed was 30 kilojoules. Okay, so let's say that the energy here is in kilojoules. Okay, so I needed 30 kilojoules of energy to convert from A to B. Okay. Next, what I did was I took B, I carried out another reaction, and I converted B to C. Okay, I converted B to C. Right, and let's say that the energy needed for this change was plus 45 kilojoules. Okay, the energy needed for this change was plus 45 kilojoules. Right, and then lastly, what I did was I took this guy C, okay, and I converted this into some substance. Okay, let's call that substance D. Right, and the energy change for this conversion was negative 50 kilojoules. Okay, so we released energy when C was converted to D. The question is what is the energy change, or what would have been the energy change had I converted A directly into D? Over here I can say that if I had converted A directly into D, my energy change would have been positive 25 kilojoules per mole, right? I can say that I can convert from A to B, right, which is 30, then from B to C, which is 45, and then from C to D, which is negative 50. And the overall enthalpy change is positive 25 kilojoules, right? And this is basically what Hess's law is saying. What Hess's law says is that the enthalpy change for a reaction, okay, the enthalpy change for a reaction doesn't depend on how many steps you take to make that product. So you can start with A, you can convert it to B, convert it to C, and then convert it to D, or you can start with A and directly convert it into D. The enthalpy change will be the same as long as your initial reactant, your initial conditions, and your final products or your final conditions are the same. So what Hess's law says is, okay, what Hess's law states is the following. Okay, this is what Hess's law states. Hess's law states that the enthalpy change, okay, the enthalpy change for a reaction, okay, the enthalpy change is independent, okay, it is independent or does not depend on the reaction pathway. So it's independent of the reaction pathway. It's independent of the reaction pathway as long as the initial and final conditions are the same. So over here in this particular example, right, if we start with A, we convert to B, we can convert B to C, and then C to D, right? And our enthalpy changes were plus 30, plus 45, and then minus 50. And the overall enthalpy change was just A to D, which was positive 25. Okay, so as long as I'm starting at point A, my initial conditions are the same. I'm starting at the exact same point under the same conditions, right? I can go from, and my final product is the same in both cases as well. So my final conditions are the same, right? I have the same products in both cases, right? It doesn't matter if I convert A to B first and then to C and then to D, or I convert A directly to D, or I go from A to C to D, right, directly, or I go from A to B and then B to D, right? The idea is that as long as my starting point and my end point are the same, the overall enthalpy change for that reaction will be the same, right? The reason Hess's law is very useful is because if, for example, I wanted to determine the enthalpy change for the reaction from A to D, but I couldn't really perform this experiment directly. However, I could convert A to B and then B to C and then C to D. I can experimentally determine these changes and then indirectly determine the enthalpy change for this reaction. So now let's look at a question. Okay, I want us to find the enthalpy change for the following reaction. Okay, I want to find the enthalpy change for the following reaction. Okay, and the reaction that we have is this one. Okay, um, so I want to find the enthalpy change of this reaction. Okay, I want to find the enthalpy change of carbon reacting with oxygen. Okay, to form carbon monoxide. Okay, to form carbon monoxide. Okay, so I want to find the enthalpy change of this reaction. And what I've given you here is the following. Okay, we know that the conversion of carbon to carbon dioxide. Okay, the enthalpy change for this is negative 394 kilojoules per mole. We also know that the conversion of carbon monoxide to carbon dioxide, okay, this process has an enthalpy change of negative 283 kilojoules per mole. So then what is the enthalpy change when carbon monoxide is formed from carbon and oxygen, or when carbon undergoes incomplete combustion to form carbon monoxide? So over here, again, we want to figure out this enthalpy change, right, which is the enthalpy change when carbon monoxide is formed from carbon. But we don't know that. What we do know is that when carbon dioxide is formed from carbon, or when carbon dioxide is formed from carbon monoxide. Now, if we're starting with carbon, we can say that we can first convert carbon to carbon monoxide through incomplete combustion, and then if we further combust carbon monoxide, we can form carbon dioxide, right? So if we go from carbon to carbon monoxide and then carbon monoxide to carbon dioxide, that's the same as going directly from carbon to carbon dioxide. Now we don't know this. This is what we have to find, right? That's our unknown, X. We know that from carbon monoxide to carbon dioxide, the enthalpy changes negative 283. And we also know that the change from carbon to carbon dioxide is negative 394. So what we can say here is that if I start with carbon, I can first convert carbon to carbon monoxide, then I can convert carbon monoxide to carbon dioxide. So here I'm going from carbon to carbon dioxide in 2 steps. But the overall enthalpy change is the same as if I were to do it in 1 step. So I can say that X minus 283, okay, X minus 283 is equal to negative 394, which tells me that, or which gives us X as negative 111 kilojoules per mole. This diagram that I've shown here is what we call an energy cycle, okay, or a Hess cycle. It's an application of Hess's law. So in this we can clearly see that we can convert carbon to carbon dioxide in 2 steps, for example, or we can convert in 1 step. The overall enthalpy change will be the same. So we can find the enthalpy change for this conversion. So now let's look at the next question. The next question that we have is here, right? We have to find the enthalpy change for the following reaction. Okay, this is the reaction that we have in the extraction of iron, right? Where iron 3 oxide in the ore react with carbon monoxide to form carbon dioxide and iron metal. Okay, and so we want to find the enthalpy change for this reaction. Okay, and we've been given the standard enthalpy changes of formation for the reactants and the product, right? We know that the enthalpy change of formation for iron metal is 0 because iron metal is an element, right? I mean, the enthalpy change of formation for elements in their standard states is 0. So we've been given the enthalpy changes of formation, and we know that the enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its constituent elements, right? So over here, right, we can say that we've been given information about the enthalpy change. Okay, we've been given information about the enthalpy change when Fe2O3 is formed from its elements, carbon monoxide is formed from its elements, and carbon dioxide is formed from its elements, right? For iron, obviously, that's just 0. Now here we're forming 1 mole of Fe2O3, right, from the elements. So we can say that the formation of Fe2O3 is negative 822. That's given to us. We have 1 mole of Fe2O3 here, right? We have 3 moles of carbon monoxide here, so that is 3 times negative 111. Remember, enthalpy change of formation Formation is for the formation of 1 mole of a substance. We have 3 moles, that will be 3 times negative 111. And in the products, we have 3 moles of carbon dioxide. So that will be 3 times the formation of carbon dioxide. So that is 3 times negative 394. And we want to determine the enthalpy change of this reaction, right? So that's our unknown. Let's call that X. The idea here is this, that we want to find the enthalpy change for this reaction, right? Let's say that's reactants to products. Now we can say that if we go from elements to reactants and then reactants to products, we go from elements to reactants and then reactants to products, that's the same as directly going from elements to products. So whenever we're given enthalpy change of formation data, okay, we can use elements to complete our energy cycle, right? We want to find the enthalpy change for this reaction, that's our unknown. And in order to complete the energy cycle, we can just use elements because we've been given information about the formation of the reactants and the products from the elements. So we can say elements to reactants and then reactants to products is the same as going directly from elements to products. You can go elements to products in 2 steps or in 1 step. The overall enthalpy change would be the same. So here we can say that negative 822 plus 3 times negative 111 plus X is equal to 3 times negative 394, right? So here we get X as negative 27 kilojoules per mole. So this is the enthalpy change for the reaction. So now let's say that I have a reaction, okay, some reaction in which I'm converting reactants to products, okay? I'm converting reactants to products and I want to find the enthalpy change of that reaction. Additionally, I've also provided information, okay, I've been given information about the enthalpy change of formation. I've been given information about the enthalpy change of formation of the products, and I've also been given information about the enthalpy change of formation of the reactants. Now, if I want to determine the enthalpy change of this reaction, I can draw an energy cycle. And since I've been given the enthalpy changes of formation for the reactants and the products, to complete this energy cycle, I can use elements, right? I know that the enthalpy change from elements to reactants is the enthalpy change of formation of the reactants, right? So that is the sum of all the enthalpy changes of formation of the reactants, right? You're going to add up the enthalpy changes of formation of all the different reactants. Similarly, I can say that the enthalpy change from elements to products is the sum of the enthalpy change of formation of all the products, right? I can say that this enthalpy change is the sum of all the enthalpy changes of formation of all the products. So what I can say is in this energy cycle, if I look at the energy cycle, I can say that I can directly convert elements to products, right? That would be the sum of the enthalpy changes of formation of the products. Or I can go from elements to products in 2 steps. I can convert the elements to the reactants first and then convert the reactants to the products, right? So what I can say here is that the sum of, okay, what I can say is that the sum of the formation enthalpies of the reactants plus the enthalpy change of the reaction itself, which is what we want to find, okay, plus the enthalpy change of the reaction is equal to the sum of the enthalpy changes of formation of the products, right? This is equal to the sum of the enthalpy changes of formation of the products. Okay. Obviously, this could be non-standard enthalpy changes or standard enthalpy changes of formation. So then what I can say is that the enthalpy change of the reaction is simply the sum of the enthalpy changes of formation of the products, minus the sum of the enthalpy changes of formation of the reactants. Okay. So if you had to find the enthalpy change of a reaction, okay, and you were given the formation enthalpies of the products and reactants, right? You could draw an energy cycle and figure out the enthalpy change of that reaction. Or since you're given the formation enthalpy data, you can just use this formula. You can use this formula to calculate You can use this formula to calculate the enthalpy change of the reaction. Okay, it will be the formation enthalpies of the products minus the formation enthalpies of the reactants, and this applies for non-standard enthalpies of formation as well as obviously for standard enthalpy changes of formation. So if we go back to the example that we just did, right, we found the enthalpy change for this reaction, right? We can use this formula to calculate the enthalpy change of the reaction as well. We can say that the enthalpy change for the reaction is equal to the formation enthalpies of the products, right? The products here being carbon dioxide. So we have 3 times negative 394. We have 3 times negative 394, right? Since we have 3 moles of carbon dioxide, right? Again, formation enthalpy is for formation of 1 mole of carbon dioxide. And then we're going to subtract the formation enthalpies of the reactants. So we have negative, subtract the formation enthalpy for iron 3 oxide, right? That's minus 822. And we subtract the formation enthalpy for 3 moles of carbon monoxide. So minus 3 times negative 111. And the enthalpy change for the reaction will again come out to negative 27 kilojoules per mole. So if you're asked to draw an energy cycle or a Hess cycle, you would draw a cycle like this for your calculation. But if you're just asked to calculate it, you can also use the formula, right, for the calculations. So if you're given formation enthalpy data, if you're given the enthalpy changes of formation for reactants and products, you can use this expression that the enthalpy change for a reaction is the enthalpy changes of formation of the products minus the enthalpy changes of formation of the reactants. So now let's look at the next question, which says calculate the enthalpy change for the following reaction. Okay, so we have the reaction shown here, and they've given us the enthalpy change of formation of this guy here and N2O4 of the reactants, and they've also given us the enthalpy changes of combustion of carbon and hydrogen. So over here again, if we're going to draw this energy cycle, we have the enthalpy changes of formation of the reactants, and we have enthalpy changes of combustion, right, of carbon and hydrogen. Right, now we also know, right, that the enthalpy change of combustion of carbon, or the standard enthalpy change of combustion of carbon, is equal to the standard enthalpy change of formation of carbon dioxide, because when 1 mole of carbon undergoes complete combustion and excess oxygen, we're forming 1 mole of carbon dioxide, right, from its constituent elements in their standard states. So let's say over here we have standard values. Okay, so we have standard enthalpy of formations and standard enthalpy changes of combustion. Similarly, we also know that the enthalpy change of combustion of hydrogen, is equal to the enthalpy change of formation of H2O, right? Equal to the enthalpy change of formation of H2O. Because again, when 1 mole of hydrogen is completely combusted in excess oxygen, we form 1 mole of water. So 1 mole of water is being made from its constituent elements, right? So now what we have is we have the formation of this guy and this guy, right, the reactants, and we also have the formation of carbon dioxide and the formation of H2O. So in order to complete this energy cycle, right, we just need elements, right? Again, because the enthalpy changes of formation are for when we are making these substances from their constituent elements. So in order to use these values, we're going to have elements here, and now we can say that we can go from elements to reactants and then reactants to products, right? Or we can go directly from elements to products, right? So this value here is, we have 4 moles of CH3NH and H2, that would be 4 times positive 53. We have 5 moles of N2O4, so that would be 5 times negative 20. We have 4 moles of carbon dioxide, so that would be 4 times negative 394. 4 times negative 394, and we have 12 moles of H2O, right? So that would be 12 times negative 288. Okay. So over here again, what we can say is that we want to find the enthalpy change of this reaction, right? Let's call that X. That's our unknown, right? And what we can say is we can look at all the arrows. All the arrows are pointing towards the products, and all the arrows are moving away from the elements. So our starting point is the elements, our end point is the products of the reaction. So we can go from elements to products in 2 steps by first converting to reactants and then going from reactants to products, or we can go from elements to products in 1 step. So we can say that this plus this, it's equal to this, right? So that is 4 times positive 53 plus 5 times negative 20 plus x, right? This plus this is equal to 4 times negative 394 plus 12 times negative 288, okay? And this will give us x as minus 5144 kilojoules per mole, okay? So that's our answer. Obviously, the enthalpy change of formation of nitrogen is just 0, right? Because it's an element in its standard state.